Hello everyone. So we already have started the fabrication and characterization techniques, and we have seen different fabrication techniques first and have started characterization techniques in last few lectures. So recently we have seen what is electron microscopy. In this regard, we have seen two different types of electron microscopy. One is scanning electron microscopy and another one is transmission electron microscopy. So we have seen that in case of scanning electron microscopy, you use an electron gun in order to get the morphological data of a certain sample. So that electron gun interacts with the surface of the sample and you detect the reflected electron beam. So this electron gun actually creates an electron beam that interacts with the surface, and then you actually detect the reflected electron beam in order to get an idea about the morphology of that particular substrate or thin film, whatever it is. In case of ACM, we have seen that the energy associated with the electron beam is comparatively less. However, in case of TEM, transmission electron microscope, the energy associated with the electron beam is much higher, and in this case what we do is you have a electron gun and then it goes through the material and forms a shadow in a fluorescent screen, and from that shadow we get an idea about the shape and size of a particular material. So it's like, as we have said, if you have a torchlight, you lit that torchlight up, then the shadow you get on the floor, from that you will be able to figure out what is the shape of the material and what is the size of that particular material. So these are electron microscopy. Similar to that, we also have force microscopies, which is known as atomic force microscopy. So in case of atomic force microscopy, what we use is a cantilever, as it is shown over here. So what we do is we have a cantilever and then we take a laser light. The laser light falls on top of that cantilever, then reflects back to a detector, as it is shown over here. So you have a laser light that falls on top of this cantilever and then it reflects back to a detector, where this detector will then determine what is the morphology of this sample based on the deflection of this particular cantilever. So if this cantilever deflects, the laser light will also deflect in the detector, and from there the system will be able to understand what is the morphology of a particular substrate. Now, one simple analogy associated with atomic force microscopy could be a blind man who has a stick. So when a blind man walks on a road, he uses a stick, and just by using that stick, he taps at different locations. Sometimes he scans using that stick different location in order to understand whether the road is smooth or if there is an obstacle, if there is a stairs in front, and based on the feedback that he gets from the stick, he visualize the morphology of the or the condition of the road, right? Similar to that, here also this acts as the stick, and then based on the deflection of that stick, then the system detects the morphology of the structure. Now the cantilever usually has a tip associated with it. The dimension of the tip is in micron. In fact, the minimum dimension of this particular tip, that is the front part of this tip, is even smaller, because you want to detect very small feature size. So the tip dimension has to be smaller than that, otherwise you won't be able to detect small feature size. What I mean by that is, for example, if you have a pattern structure like this, where the dimension of this feature is say 10 micron, then if you use a tip in order to detect this structure, the tip dimension has to be less than 10 micron. If it is more than 10 micron, say you have a tip like this, then it can't detect this particular structure. It can't detect this 10 micrometer difference. So the tip dimension has to be very small. So this particular force microscopy works in 3 different modes. One is contact mode, another one is tapping mode, another one is non-contact mode. So in case of contact mode, the tip comes in contact with the substrate and starts scanning. So if there is a particle present on the substrate, so the tip will start scanning and definitely it will deflect when the particle comes in contact with the tip. So this way the system will be able to understand that there is certain sort of obstacle present in the particular substrate, right? Now this is a destructive method, because if you use a soft material on top of a substrate, say thin film of a soft material, then it will create a scratch on top of that material, which is not desirable in many cases. So if you are planning to use contact mode, then you can't use that sample for some other application, because this will anyways destruct or destroy your sample in various locations, because it is coming in contact with the material. So it may create scratches. Okay. The next method is tapping method or tapping mode, where the tip doesn't come in continuous contact. What it does is it like taps at different locations. So it taps at different locations, and from the tapping it will be able to understand whether there is a particle present on the substrate or not. Particle or any structure, uneven structure is present on that substrate or not. So tapping mode to some extent is non-destructive. Then you also have another mode which is known as non-contact mode. In this case, the tip comes very close to the substrate, and then based on the interaction between the substrate and the tip, mechanical interaction, or sometimes it is like electrical interaction. If there is a current flowing from the substrate to the tip, then it's electrical interaction. Otherwise it's a mechanical interaction like attraction and repulsion force. Based on that, it will be able to detect the morphology of the structure. So these are the 3 different modes associated with the atomic force microscopy. Now if you define the entire thing using a plot, you will see that any 2 objects, when they come close to each other, it follows this particular trend. The force between these 2 particles will follow this particular trend. If the distance is very less, then there will be a repulsive force associated with this. Then beyond a certain distance, there will be certain sort of attraction, and then as we move away from or keep those particles away from each other, the attractive force will keep on reducing. Now the tapping and contact mode actually takes place in this region where the attraction force is there, and then the non-contact mode is usually in this area where there is certain sort of attraction force. So here all 3 types are explained schematically. For example, in tapping mode, it taps, keep on tapping, and then when there is a feature size or a particle, when there is a feature present on the substrate, it will again tap. So from that tapping itself, it will be able to detect the morphology. This is the contact mode where it is always in contact and then goes like this. Then in non-contact mode, it doesn't come in contact with the feature or the substrate. Based on the interaction only, it will be able to detect the morphology. This is what is atomic force microscopy. Now there is another microscopy similar to that, which is known as scanning tunneling microscopy, where your substrate has to be conductive, and then you apply a potential sufficiently large between the tip and the substrate, and then based on the feature size, there will be a tunneling current which will vary. based on the feature size, as I have said. So if the feature size is like that, like this, then this distance will reduce, so current will be higher. If the feature size is like this, then distance will be higher, so the current will be less, the tunneling current will be less. Now from this tunneling current, you will be able to figure out what is the type of substrate or what is the morphology of that particular thin film over a substrate. So here I have given you different type comparison between different types of microscopy that we have discussed. So in case of ACM, the lateral resolution is 5 nanometer. Anything less than 5 nanometer is very difficult to get from a scanning electron microscope. In case of TEM, it's 0.2 nanometer, which is very small. And then in case of STM, it's even smaller, 0.1 nanometer. For AFM, the lateral resolution is usually 30 nanometer. So if you want a very small feature size, or if you want to detect a very small feature size, it's better you use TEM, transmission electron microscope. But you also have to remember, in case of TEM, you need a TEM grid in order to analyze your sample. Usually nanoparticles, nanostructures that you synthesize in a solution method, TEM is best for these kind of samples. If it's a thin film over opaque substrate, then ACM is the best method to detect the same. If there are a lot of features present in the substrate and you want the information regarding height of that feature at various locations, then AFM is again the best one to use. But in case of AFM, the tip usually scans a very small area on that substrate, and if the surface is very rough, because it is tip based, if the surface is very rough, this may also destroy the tip. So in order to take a sample on a AFM, you have to ensure that the roughness is not very high. The roughness of that surface is not very high. So this is one consideration that one has to check. As far as the vertical resolution is concerned, in case of ACM and TEM, you don't get that vertical resolution. You only have lateral resolution. However, in case of STM and AFM, you will be able to get a vertical resolution, because as I have said, it can detect the height of the feature size as well, because it's in contact and deflection based. So you will be able to detect 0.1 nanometer also, as far as the vertical resolution is concerned. In case of STM, it is 0.01 nanometer. In fact, using STM technique, you can manipulate molecules on top of substrates. You can take one molecule to other place and can actually align different molecules or atoms for that matter. Okay. As far as the magnification is concerned, in case of ACM and TEM, it is 2D magnification, X and Y. However, in case of STM and AFM, it's 3D, X, Y and Z. In all three directions, you will get the information. Now, as far as the sample preparation requirement is concerned, in case of ACM, you need gold coating. If the material is not conductive, you need to coat that material using gold or a conductive non-reactive material, so that charge accumulation is not there. If charge accumulates on top of the substrate, then the image contrast will not be that high. Then you need a carbon tape in order to attach the substrate on the sample holder. In case of TEM, you need a specific TEM grid, TEM grid. As we have seen, the TEM grid is nothing but a mesh where you put the sample and then you scan all these mesh. And in case of STM and AFM, you just need clean surface, so that there is no kind of big particles on top of your substrate which can actually destroy the tip. So you need a clean surface. When you prepare the sample, you make sure the sample is clean. As far as the operation condition is concerned, in case of TEM and STM, it's a vacuum process. However, in case of ACM and AFM, this can be vacuum or environmental. So both the options are available. Now, as far as the cross-sectional image is concerned, for example, you have developed a thin film over a substrate. So this is side view. So this is the substrate and this is the thin film. Now if you want to take this cross sectional image, in case of ACM and TEM it is possible, but STM and AFM will not be able to give you a cross sectional image. In case of ACM and TEM, you have arrangements where you can actually tilt the substrate and can image the cross section of a particular sample. Okay, so these are the comparison of various electron microscopy and force microscopy. Now there are different material characterizations also. For example, Raman spectroscopy, UV visible spectroscopy and XRD. These are widely used material characterization techniques for sensor applications. So in case of Raman spectroscopy, it works based on Raman scattering. For UV visible spectroscopy, it works based on optical absorption, and for XRD, it works based on X-ray diffraction. Using Raman spectroscopy, you will be able to get chemical structure and its identity. It will be able to detect phase and polymorphism. It is also capable of detecting intrinsic stress and strain. It can also detect contamination and impurity of the sample. Similarly, using UV visible spectroscopy, you will be able to detect to some extent chemical identity. You can also detect contamination and impurity. You can detect the optical bandwidth of that material and then absorption wavelength. So you also can say at what wavelength the absorption is higher, the optical absorption is higher. Then using XRD, you will be able to detect the chemical identity, you will be able to detect contamination and impurity, and then most importantly, you will be able to detect the crystallinity of a material, that is crystal planes, what type of crystal it is, this type of information you will be able to get. So I am not going in details of these material characterization techniques, but as I have said, using these material characterization techniques, you will be able to get these informations. There are several other material characterization techniques like FTIR and different other, for example, XPS and etc. I am not going to these details, but these are the basic material characterization probably you will find in case of sensor fabrication and sensor characterization. Apart from that, you also will find different electrical characterization associated with that. You are aware of different electrical characterization equipment if you already have done labs in electrical engineering. So there are multimeters, digital multimeters, there are source meters, there are vector network analyzer, there are parametric analyzer, there are impedance spectroscopy, there are different LCR meters that can actually be used for electrical characterization. However, equipment is decided based on the phenomena or physics associated with it. For example, if it is a resistive sensor, a digital multimeter should be sufficient. A high resolution digital multimeter should be sufficient. If it is capacitive sensor, you may need LCR meter, and so on and so forth. So these are the other characterization techniques associated with sensor technologies.
As far as the microscopy techniques are concerned, we have seen that there are three different types. Mostly one is optical, then you can use electron beams, and then you have force microscopy, right? So in the optical microscopy, we've seen that the resolution is a problem. We can't go below certain resolution, and hence electron microscopy is needed if you really want to image very small feature sizes, say in the range of nanometers. Then it's better you take help of electron microscopy, where electron beams are used in order to image a surface. However, in case of optical microscopy, the imaging is done by the optical signal or light. Uh, in brief, if we say, then light is the major component of imaging in case of optical microscopy, and then you can maybe image feature sizes up to say 1 micrometer or maybe a bit less than that. However, in order to achieve a resolution of 1 micrometer is itself a challenge, because the working distance between the objective and the sample, that distance becomes very very less. So that is why there are some practical problems that we need to face in case of optical microscopy if you go below certain length scale. However, in case of electron microscopy, we can image things in nanometers. For example, if you take transmission electron microscopy, we also at times can image different crystal planes. We call it HRTEM, that is high resolution TEM, and then you can figure out different crystal planes on a sample, which where the length scale is of the order of say angstrom or so. So you can actually achieve a very very small resolution, which probably is difficult, or in fact theoretically also impossible using optical microscopy. So we have a huge advantage of having electron microscopy. Then we have force microscopy. We already have seen some of the comparisons in the previous discussion or the previous slide in this lecture itself, but just reiterating the same thing to give you an understanding that what are those options that we can use as far as the imaging is concerned. So in case of force microscopy, you also can image things in 3D, so you get an information of height as well. So this has its own benefit. For example, if you have a substrate like this, and if you go to AFM, that is atomic force microscopy, you'll be able to figure out what is the height of it, because in this case the entire imaging is done using a tip, which is similar to you know a blind man scanning a surface. So he also uses a kind of stick and then taps it in different location in order to find how the surface is ahead of him. It's so close to that particular phenomena, and then actually you can get information about that substrate in 3D. That is not possible in case of TEM or FEACM or ACM, right? So these are the imaging techniques, and one has to decide the imaging technique based on the need. If you need a very small feature size, you can go to TEM and then image the same. But the thing is, sample preparation in TEM is not very straightforward. So in case of TEM, you have a small grid, we call it TEM grid, which has mesh, and then you drop cast the sample on top of this, and then it will create a kind of uh, film over that template. Not film exactly. What it does is like the particles or whatever sample you have will get stuck into that mesh, and then you put it under the microscope, that is TEM, transmission electron microscope, in order to image the same. But in this case, in case of TEM, the samples that generally are used is like nanostructures and nanoparticles, and you have to prepare the sample in a solution media so that you can drop cast the same on top of TEM grid. However, in case of FESEM, you actually can take a thin film over a substrate, say glass substrate, silicon substrate. Okay, and then that thin film you can put under the scanning electron microscope to image the same. So that is how the samples are in case of both the microscopy. Even if you want to characterize the size of a nanoparticle using ACM, in that case you can drop cast the nanoparticle solution on a substrate in order to create a film kind of on top of a substrate, and then you can take it to the FEACM. But in ACM, if you want to image a feature size of say 10, 20 nanometer, 30 nanometer, or so, it's very difficult, because that much magnification uh, in FESEM is very very difficult. In fact, you can get an idea about that structure, but going deep down into that uh, length scale is really really difficult. However, in case of TEM, you can very easily measure 20 nanometer, 30 nanometer particles with proper shapes, whether it is spherical or triangular or elliptical, whatever it is, you can see that in that particular image. So this is what different imaging techniques are concerned. And in conclusion, what I would say is, one should actually decide the characterization facility based on the sample in hand. If your sample is thin film and you do not need very small details on the surface, then it's better you go to SEM. In most of the cases, if it's a device, now you want to characterize the device electrode and etc., you can do it with optical microscope first. If you think that under optical microscope the device structure is more or less okay, then to get more details, even details in micron range, you can also characterize the same using FESEM. Okay, so once you characterize the same using FESEM, you'll get an idea about the active material thin film or electrode in a micrometer range. So that is how one can characterize the device after the fabrication is done. So this is possibly the first step after you fabricate something, because once you fabricate a device, it's very important to know whether the electrodes are formed or the device structure is properly made or not. Say you want to develop a device where these are the two electrodes and then you have some other layer beneath, so you first have to check whether this structure is formed or not. That's why after preparation, it's better you go to FESEM and check the device structure. Thereafter, you can check the elemental analysis. Elemental analysis meaning what are the materials present over there, whether there is any contamination, whether the material got oxidized or not. For example, if you are using aluminum electrode, there is a high chance that after reacting with the ambient air, the aluminum will convert into aluminum oxide. In that case, it's very very difficult to get a good response out of that electrode. So it's very important you do your morphological analysis. Morphological analysis means analysis of the surface of your device. Then you go to elemental analysis. So I already have mentioned what are some techniques by which you can actually do material characterization. So you can go to Raman spectroscopy. There are UV visible spectroscopy, then XRD is there. Then you can do EDS also. So EDS is a system which is usually connected to FESEM itself. So once you do morphological analysis, then and there you can actually check the elemental characterization, you check the elemental composition or the material present on that particular device at various locations. So that is one way to do both the things together. So you can do an EDS analysis to cross check whatever material you intend to deposit or intend to put in your device are there, or it is contaminated or oxidized. Whatever is the situation, you can actually check using that analysis. And once that is done, then you can take your device for electrical characterization. So in case of electrical characterization, again you have multimeter, then you have oscilloscope, then you have say VNA, then you have parametric analyzer. So all these electrical characterization you can do once your device is properly made in order to check the electrical response of the device. So most of the electrical characterization equipments you probably have seen, at least the basics one like multimeter and etc. you have seen, and you can actually get an idea about those characterization just by the experience that you have got in your say basic electrical lab and electrical labs as a whole. So this is in a nutshell what the characterization techniques are, especially in case of microfabrication or sensor characterization.
In the upcoming discussion, we will start system associated with sensor. We'll see what are the basic systems associated with a sensor technology, and we also will see what are the different blocks associated with a sensor system. Till then, thank you.